Hi, so in this video we are going to see an example of the 0-1 knapsack problem. So let's get started. The typical situation is like this. We have the so-called knapsack table with the weights and the items. We have n equals 3 items and we have a maximum capacity of the knapsack m equal to 5 kilograms. So we can put up to 5 kilograms into this knapsack. We cannot put 6, 7 or 8 kilograms because we cannot exceed the capacity of the knapsack when putting items in it. So the item 1 has a weight W1 4 kilograms and it has a value V1 $10. The second item has a weight 2 kilograms and it worth $4. The third item has a weight 3 kilograms and it costs $7. So the knapsack table, the column represents the weights 0 to the maximum capacity of the knapsack, and it is an integer programming problem, so we cannot have 2.5 kilograms. As I said earlier, it is not the first problem, the dividend knapsack problem. We saw that the greedy algorithm is feasible. We can use the greedy algorithm, but in this situation we cannot use the greedy algorithm because we have to choose whether to take an item or not, and that's why it is an integer problem. We have integer weights and integer items. So the columns represents the weights and the rows represents the items. And because we have subproblems, we have a subproblems when there is no items. It's very easy because we are going to fill the table with zeros, because if there is no items, of course we cannot put anything into the knapsack. And then we have only a single item with index 1, and we solve the subproblem and assume we have only one item. Then we assume that we have the first two items, and we are going to rely on heavily on the previous row of the knapsack table, and this is why we call it dynamic programming, because we are going to rely on the previous row's information. So we keep updating rows by rows, and we come to the conclusion that we can get the feasible solution with the help of dynamic programming. Of course, we are going to get the situation when we have to consider all items, item 1, item 2, item 3. So let's get started. And of course, it's worth considering, mentioning that it is the magic formula in yellow, that AIW equals to the math.max AI minus 1W. This is a situation when we do not take the item with index I, and of course there's a situation when we take it, so we have to, there's a VI representing the value plus AI minus 1, V minus VI. So in this situation we take the item with the ith index, so we get the value with VI, and we have to subtract the VI weight from the knapsack's weight. So let's get started. We have to update the tables, so if we have no items, of course we have to fill it with zeros. And of course we have, if there is zero weight we can carry, of course we cannot take any items because all the items have greater weight than 0. So the first row and with index 0, and the first column with index 0 is going to be null. So let's get started. If we have only one item, the first item that has 4 kilograms and it has a value $10, of course we cannot put into the knapsack if it can carry only 1 kilograms. So the header of the columns represent how many kilograms the knapsack can take, And in this situation, 1 kilograms and 4 kilograms is greater than 1, so we put a 0 in this position. If we jump to the third row with index 2, it represents that the weight is the capacity of the knapsack can carry 2 kilograms, and 4 is greater than 2, so it is 0. 3 kilograms is less than 4, so it's 0. And we come to 4, we see that the first item weight is 4 kilograms, so if the capacity of the knapsack would be 4 kilograms, then we can take the first item, and for the first item we get $10, and that's why we put 10 in this location. The next one, it is the knapsack in this situation can carry 5 kilograms, but we have only one item, and this item has only 4 kilograms, so we can put the 4 kilograms in a 5 kilograms capacity knapsack, and we get the value, which is $10. If we have two items, we can rely on the formula, the magic formula, because in this situation and from this situation, these kind of calculations are not so straightforward. So we can use our equation, and in this situation, our equations tell us that the A with row index 2 and column index 1, we have to consider the maximum of two integers, the A11, which is we can look up in the table the row index 1 and column index 1, there's a 0, and the second item is $4 because that's the value of the second item, plus the A1, 1 minus 1, and because the index 1 minus 2 is equals to minus 1, and our table, it starts at 0, it is an invalid index, so we consider it 0. So we have to decide the maximum between 0 and 0, which is 0. So we put a 0 to the A row index 2, column index 2. We jump to the next column, and it's going to be 4. Why? Because A22 is equal to the mass that max with index A, 1 and 2, which is we can look up in the table. It is the row index 1 and column index 2, there's a 0. And the second integer will be $4 plus A, 1, 2 minus 2. We can look it up in the table. The row index 1 and the column index 0, there's a 0, so $4 plus 0 is equals to 4. We have to decide between 0 and 4, so it is the 4 because 4 is greater than 0, so we put a 4 there. Jump to the next column. It is a 4. Why? Because we have to calculate our magic equations or magic formula. A23 is equal to the mass that max. We can look up the table, the A with row index 1 and column index 3. It is, of course, 0, and we calculate the $4. Why $4? Because we're considering the item with the second index, so the second item, and the second item has a value of $4. So $4 plus the value in the lookup table with row index 1, column index 3 minus 1. If we look it up, we come to the conclusion that it is 0, so $4 plus 0 is equals to 4. We have to decide whether 0 is greater or 4. We come to the conclusion easily that 4 is the integer we are looking for, so we put it into the right place. Okay, the next one is 10. Why? Of course, again, we just have to calculate our formula. So A with row index 2 and column index 4 is equal to the mass that max A14, which is 10, and we have to calculate the other situation when we take the item. So it's very important that the first integer in the mass that max equation represents that we don't take the item with index I. In this situation, index 2, so we cannot take the item 2. In the equation, the $4 plus A 1 and 4 minus 2 represents the situation when we take the item with the index 2, so we take the second item, and we have to calculate that is it a good option if we take it with us or not. So this is why we have to calculate on each iteration. And A with row index 1 and column index 2, it is a 0, I think. Yeah, it's a 0, so 4 plus 0 is 4. So we have to decide which is the greater, 10 or 4, and it is 10. So we put 10 in this location. The next one is also 10 because we have to calculate the in the lookup tables, we just have to look up the integers, row index 1, column index 5, it is 10. And we have to calculate the row index 1 and column index 3, which is 0. So, 0, $4 plus 0 is 4. So we have to choose between 10 and 4. We have to take the maximum of these two numbers, and we come to the conclusion easily that it is 10. So, we keep updating our table like this, and we do it for the last element, and of course it is for the row index 3 and column index 1, it is 0. As I said earlier, if we have the situation like in here that we want to calculate the A with row index 2 and column index 1 minus 3, we wanted to calculate something where the column index is less than 0. In this situation, we consider the whole stuff to 0, no matters that there's a $7 in the beginning. So it is 0, and A21 is also 0, so it's going to be 0. The next item is going to be 4 because we calculate the mass.max. The second row index and second column index, there's a 4, and because the index is less than 0 on the second expression, so we take the 4 because it's greater than 0. Then it's 7. Why? Because in the lookup table, the integer with row index 2 and column index 3, there's a 4, and integer with row index 2 and column index 0, there's a 0, but $7 plus 0 is equal to $7, and 7 is greater than 4, so it's going to be a 7. Then it's going to be the 10, because we have to look it in the tables, and we come to the conclusion that we have to decide between 10 and 7, and 10 is greater, so it's going to be 10. And in the last row index and last column index, it's going to be 11, because the row index 2 and column index 5, there's 10, and we have to look up the knapsack table with the row index 2 and column index 2. It's going to be a 4, so $7 plus $4 is going to be 11, and because 11 is greater than 10, it is going to be the winner. So we have filled our knapsack problem, our knapsack table. So the solution is the item in the last row and last column. I colored it with red. So we come to the conclusion that the optimal solution, if we take the optimal items, we can get $11 at the maximum. So it is the feasible solution. But another good question is what items we have to take, because from this knapsack table it's not straightforward what items we have to take. And we start at the item, the 11, and we have to check whether the integer on the previous row, so the 10, the row index 2 and column index 5, there's a 10, and we have to check whether we have inherited that integer in the next row, and we come to the conclusion that 11 with red color is not equal to 10. And that's the point when we come to the conclusion that we have to include item 3. And we have to jump to the previous row, but we have to, of course, it's kind of a backtracking. 11 is the value, and we have to subtract the value from this 11 and the value of the third item. And the third item value is 7, so we have to subtract 7 from 11, and it's going to be 4. So we have to find this 4 on the previous row. That's the neighbor of 11. I mean, that's the distance is the minimal between this 4 and the 11, because there's another 4, but we have to check that's closest to the 11, and that's going to be the 4, and we have to check whether we have inherited this 4 from the previous row with row index 1 and column index 3, and we come to the conclusion that in that position there's a 0. So row index 1 and column index 3, there's a 0. 0 is not equal to 4, so we come to the conclusion that we have to include this item too. And because the value of the second item is equals to 4, we can stop, because if we subtract 4 from 4, we get a 0, and that's the termination point of our backtracking algorithm. During implementation, it will be clear that it's just a simple for cycle. We have to decrease the weight, we have to decrease the values, and we can find our solution like that. So like this, with the help of a knapsack table and with the help of dynamic programming, and with the help of memoization. It's kind of a memoization because we keep track of every row index and column index, the given value we can get at the maximum. And in this lookup table, this so-called lookup table, we can get this information in constant time, and that can make sure that the algorithm is as fast as possible. So to summarize, we managed to solve our problem, and we get to the conclusion that if we have 3 items and the capacity of the knapsack is 5 kilograms and the weight of the first item is 4 kilograms with value 10, the second item's weight is 2 kilograms with value 4, and the third item weight is 3 kilograms with value 7, then the maximum value we can get with the help of this knapsack is $11. Why? Because it is the we can get it from the knapsack table at the last row index and last column index, and we can get what we want to find, what items we have to include in our knapsack. We start from this 11, so at the last row index and last column index, and we keep backtracking and get to the solution that we have to take the item 3 and item 2, and if we check that item 2 and 3 has 5 kilograms as far as weights are concerned, and it has a maximum value of 11, so our solution has been checked. That's the knapsack problem with dynamic programming. In the next video we are going to implement it together. Thanks for watching.